Hi there. I want to do a couple of videos on curve fitting, and I'm going to start at the beginning, something very simple, just linear regression. And since people seem to like financial videos, we're going to start with finding the beta value of a stock, Apple in this case. It's pretty straightforward. I almost didn't want to make this particular video because it's really easy, but I think it'll lay the groundwork for more complicated things going forward. So let's get started. We're going to do the coding in Python, but before we get started with that, let's do a little bit of background material first. The problem we want to address is we have a collection of data and we wish to represent that by some line, or at least we think the data has some sort of linear relationship and we want to try modeling it with a straight line. Now the plot to the left doesn't look particularly linear at first glance, but I had the computer generate a line and then add some random noise to it. So this is in some way representative of real world data. Your models are not going to be perfect. You're going to have statistical outliers. And perhaps in one of the companion videos, I'll talk about different methods of doing like linear regression that in some way addresses the possibility of outliers. So moving on, our task is to find the equation of this line, to find the slope and intercept of this line that in some way represents some sort of best fit to the data. Now it's a bit arbitrary how you define best fit, and you do have leeway in determining what criteria you are fitting to or what constitutes a best fit. What we're going to use here is the typical least squares method. What that means is we're going to look at the error between each data point and the straight line representation. That's shown here as these epsilons, for example. Where's my cursor? Here we go. This third point right here, labeled as epsilon 3. This gray line represents the distance between my actual measured data point and our model. So this represents the error, and what we want to do is square this error and sum up the squared error for all these data points, and then we're going to choose the slope and intercept that minimizes that squared error, hence the term least squares method. So to make this a little bit more formal, let's go back to high school and recall that the equation of the straight line is this. It's y equals mx plus b, where m is the slope of this line here, and b would be the intercept, the point where it crosses the y-axis. So that's straightforward. So to calculate the error from between each data point on this line, we just take the y point of this line, which is in this case, the third point, y sub 3, or in general, the ith point, so y sub I, and then evaluate the line at this point, like x sub I or x sub 3 in this particular point here. And that's what this expression is. It's y sub I minus the quantity m x sub I plus b. So that's the error between any given data point and the model. Now we're just going to square that, add them all up down here, and wait for this thing to vanish. There we go. Add up all those squared errors, and then we're going to try to find the minimum of that. Choose m and b such that that's at a minimum. It turns out that this type of problem here, at least this simple linear problem, can be solved by pencil and paper, and perhaps in a companion video I will do that derivation. But we're just going to have the computer do it, and again, for linear problems, it's pretty straightforward. All the programming languages I know of have built-in linear regression algorithms, and things like Excel and Google spreadsheets have linear regression algorithms built in, and they can just spit out the answer for you. So we're going to look at Python and have it provide an answer for us. And I should probably say the reason I'm harping on this little bit of mathematical stuff here, when it's something the computer is just going to spit out an answer to anyways, is that in the real world a lot of problems are not linear, and the computer is not going to be able to have a built-in model for you to just readily plug in your stuff and get an answer out. So you're going to have to code it by hand. So later on I want to address those models and look at situations where we don't have these readily available canned routines for us, and we're going to have to build the code from scratch ourselves. As I mentioned, a lot of languages and software packages already have a linear regression function built into that, and in Python, the SciPy stats module has a function called linregress for, not surprisingly, linear regression. And so that's what we're going to use, and this whole thing is going to boil down to essentially one line of code, and then the rest of the code is just stuff to import the raw data and put it into a form that we can use. So the problem we're going to address is to find the so-called beta coefficient of Apple stock. So on the left-hand plot here I have price data for Apple for the last 5 years, and the right-hand plot is the S&P 500 index, the SPX. So what we're going to do is calculate the day-to-day percent change of Apple and plot that as a function of the day-to-day change in the S&P 500 index. And eventually we're going to fit a straight line to that, and the slope of that line is the beta coefficient. The interpretation of beta is basically a measure of, for lack of a better word, volatility risk, assuming the stock and the index move in the same direction, which is going to move more and by what factors. So you might think a high-flying tech stock would be more volatile than the index, and if the index were up 1%, maybe the stock is up 2, and vice versa. So beta is essentially a measurement of that type of volatility. So here's a plot of that percent change, day-to-day percent change of Apple versus percent change of the S&P 500 index. And you can see it's just kind of a mess that follows kind of a linear trend, but it's kind of just like a big blob of data that more or less follows some sort of linear relationship. So what we're going to try to do is actually calculate the slope of that linear relationship, and that's shown here in the by the solid line. So let's get on to coding here. We're going to need our NumPy libraries. So import NumPy as NP. We're going to import the SciPy stats library, and we're going to import a library called pandas, which is going to handle importing the CSV files that contain all our data for us, and we're going to use it to just do like calculate the percent change, so we don't have to actually write the code to iterate over it. We can just calculate it with one command via pandas. And I'm going to put in the matplotlib libraries just in case we want to plot anything. Now I've already downloaded from Yahoo Finance CSV files that contain data for Apple and SPX, and so here are the actual files. So we're going to use the pandas library to import these. So let's first of all just, how do I want to do this? I want to do that, and I'm going to call this variable AAPL underscore frame for the data frame that contains this these data. And a data frame is just basically a tabular data structure that contains different forms of data in different columns. So it could be like a string of dates in one column, and so on, prices in another. And we're going to use the pandas function read CSV. So let's do that, and let's change this instead of APL to SPX. So there we go. Let's just make sure I haven't got any typos by running that. Good, we're good to go. In fact, before moving on, let's move back to our code and let's take a look at the data in this in these frames. So I am just going to print out AAPL frame. Oh, I cannot spell today. Frame, and I'm going to use the head command to just print out the first few lines of that data table. So there we go. You can see it's just tabular data. You have a column for dates, then opening price, high, low, close, and then adjusted close. So Apple has split a couple times since, well, it's split at least one time in that period, or actually maybe, geez, I don't really remember when it split. It split 7 for 1 in relatively recent years, but it's also adjusted for dividends and things like this. So we're actually going to use this adjusted close price in our calculation. So okay, now we need, let's just get rid of that line, and we're going to need the percent changes of these the Apple and SPX data. So AAPL, and I'm just going to call it underscore PCT for percent, and that is going to be the AAPL frame, and we're going to get the adjusted close column, ADJ close, and Pandas is very convenient in that it has a function called PCT underscore change, and it's going to do what you would think it does, just calculate the percent change. Now this function actually returns another pandas data frame, and we want a numpy array to eventually pass to our thing, and we can get that by using the command values. Now that we have that, we could do the same thing for the SPX. Something looks funky here. Oh, I need a closing quote here. So let's just be lazy now, and to do the XPX data, we'll just change. We'll use the text editor to change AAPL to SPX, and that should be good. So let's go to our console. Let's just make sure that this runs. I have a habit of making typos, and PCT. Where? Come on. Oh, I see what happened. It's PCT underscore change, and I was a little too quick on the keyboard. Here. Now it should run. There we go. Okay, and we're all set to go, but actually before that, let's just plot this data out. Plot, our x values are going to be SPX PCT, and our y values are going to be AAPL underscore PCT. And let's make these, I don't know, blue dots. And then do a plt.show. Save it. Console window. Yeah, and that looks basically like we would expect it to look. So now we're ready to move on. Okay, let's get rid of this for now. We don't need it at the time, or at the moment. And let's actually calculate our beta value. So save. So now we're ready to actually calculate beta. So our function is going to return a bunch of values. The slope and intercept are what we care about. These other values here, like RP, the standard error, for this video we don't really care about those. So now we go to our stats, win, regress, and our x values are the SPX, percent change, and AAPL PCT. Let's just make sure that runs. Stats is not defined. How can that stat? Oh, I see, up here. This should be from SciPy, import stats. Oh, okay. We have one other issue here, and that is that in calculating these percent changes, it's a day-to-day percent change, so it's putting not a number for the first value, because obviously you lose a day because you have to go like percent change from your first day to the second day, and then obviously you don't have a number for your first day. So we have to go through and delete the first index of our matrices or our vectors, both for Apple and SPX. So let's go back down here, and I just copied this and pasted it from a test script. So now we should be able to run it. Yay. So now let's print out the results. So let's print beta equals, and then we want to print out the slope. That's our beta value, slope. Let's go to our console. There we go, a little over 1.2. And before calling this quits, let's just plot out this stuff. So let's go back down here to our plot. Let's uncomment this, and let's make these blue dots a little bit transparent. So alpha 0.2, just so it's not a huge mess. And I also like to turn the grid on. So plt.grid true. And now let's see. Let's come up with some x values. So x is going to be the minimum percent change of the SPX. So let's just do np.amin. This is actually going to be np.lin space the minimum value of SPX percent change, and on the top value, the last value is going to be np.the maximum. np.max SPX PCT, and that should be that. And then our y values is going to be just the slope times our x values plus the intercept. So there's our x and y values. So let's go back to our plot. plt.plot x comma y, and we'll make this a black line. And we'll see if I've screwed up anything here. And of course I have. What happened here? Why is... I probably never finished out this... let's see. Oh, I never finished out this... finished off this parenthesis here. And there we go. It's basically the same plot I had in these slides. So yeah, linear regression. That was pretty straightforward and simple enough. I'm going to do a couple videos on curve fitting and regression type things in general. I think the next one or two, probably the next two, are going to be pretty straightforward. I want to just do a derivation. I said that this linear regression can be done by hand with paper and pencil. So I probably think I'm going to do that derivation. It's the kind of thing, you know, the computer does for you, but you should probably at least do it once in your life and just understand, you know, how these things come about. And the second one is going to also return to the same data set and be a linear regression. However, to build up to more complicated things eventually, I'm going to pretend that we cannot, this model is not linear, and that we cannot use some sort of canned fitting routine. So we'll come up with a model error function and minimize the sum of the squares using nonlinear minimization routines in SciPy and NumPy. So yeah, that's about it. Yeah, great. Talk to you guys soon.